All right, guys, hope everybody's doing okay. This is Mr. Krowski. Today we're going to take a look at something called the Born-Haber cycle. This is really going to focus on the formation of ionic compounds. So we know basically how that works, but we're really going to look at the energy involved here. In a later lesson, we're going to look at the energy involved when we create covalent molecules. So it's a big chunk of this first unit here where we look at that. So we're looking at ionic and covalent bonding, and we're looking at the energy changes that are involved with that. So let's get right into it here, and we'll start with just an introduction here, quick review of what ionic bonding is all about. So types of chemical bonds that we have. Ionic, one of them, right? So electrons are transferred. We talked about this back in Chem 1. So you have electrons being completely transferred from one atom to another. That's because one atom has a much higher electronegativity value than another one does. So there's this very unequal want of electrons. So one atom tends to kind of rip them off of another atom. And that's how we get those full charges. So you typically have this occur when it's a metal bonded to a nonmetal. Covalent bonds, which we'll focus on a little bit later, that's when electrons are shared, sometimes equally, sometimes unequally, and that's when we have all nonmetals, and when we have covalent bonding. So ionic is the focus of the day here. So electrons are transferred from one atom to another to produce an ionic compound. So here we have table salt, NaCl. You can see sodium with its 1 valence electron, right? Chlorine with 7. So chlorine has a very high electronegativity value, one of the highest on the periodic table, and sodium has a relatively low one. So we're going to transfer our 1 valence electron from sodium to chlorine. I'll do it one more time so you can see it move. And what happens now? Well, sodium becomes a positive 1, plus 1. It lost a valence electron. Remember, electrons are negative. Chlorine went from 7 valence electrons to 8, so it gained 1, so there's a negative charge. And now look, we have opposite charges. Opposite charges attract. We know that from Coulomb's law. And here they go. They come together. So that's how table salt is formed. Okay, it happens over and over again. You have this big crystal lattice structure of NAs and Cls. Okay, so the opposite charges attract to form the ionic bond. That process that we just saw here, that is what we're going to look at today, and we're going to look at the energy changes along the way for this to occur. So, before we get into that, describe the electron transfer that occurs in the formation of magnesium fluoride. So you need to think, what is the formula for magnesium fluoride? So magnesium fluoride is going to be MgF2. Right? Magnesium would form a +2, fluoride would form a -1. So how is this going to occur then? Because you have Mg, magnesium has 2 valence electrons, and fluorine has 7. Okay, 1, 2, 3, 4, 5, 6, 7. All right, so how's this going to occur, right? So you have 1 electron from magnesium going to move over here and be transferred. Remember, fluorine has the highest electronegativity value. Fluorine's a 4.0, so it's going to steal electrons off of babies, right? So now fluorine has an octet. Magnesium lost an electron. We can't have the other one go to this fluorine because that would be too many valence electrons, right? So, the formula is MgF2, so we have another fluorine atom. Okay, 7 valence electrons. Electron goes here. Okay, so what answer is the correct answer then? Looks like number 2. Each magnesium atom loses 2 electrons, and each fluorine gains 1. Okay, and you can see that here in the little sloppy diagram I have for you guys. All right. Okay, before we get into the Born-Haber cycle, one last thing. Quick review on energy. If you don't understand this, if you forget this from Chem 1, this is going to be a disaster. Okay, so if energy is given off or released, what does that mean? Like, where is that energy term going to be written? That's an exothermic process, and the sign on the energy change is negative. Okay, so your delta H or your delta E is negative. All right, Negative just means released, okay? It's not like you have negative energy or something. It's a release of energy, okay? And that's found on the product side of a reaction. So you would have, if you had something, right, yields something plus, 40 kilojoules. That means, mouse is all hung up here. That means that 40 kilojoules is released in this reaction, okay? It's on the product side. So 40 kilojoules being released or given off when this occurs. You're going to say, where's the negative sign? The negative sign just tells you that it's being released. That means we put it on the product side. So the overall energy change for this reaction would be negative 40 kilojoules. Okay? You're never going to see a negative energy value in an equation like this. Okay, so that's important here. So if they said the delta H is negative 40 kilojoules, that tells you that it goes on the product side. Okay, if they said the energy change was positive 40 kilojoules, it would be on the reactant side, which is what we have here. So if energy is added, used, required, that's endothermic. The delta H is positive, and it's on the reactant side. So if you had some process, and I said the delta H was positive 40 kilojoules, then you would have something plus 40 kilojoules yields something, okay, whatever it is. Okay, so you can see delta H is negative, it's on the product side. Delta H is positive, it's on the reactant side. Easy money, okay? That's all you got to remember here. A lot of this will just kind of fall in place for you. But exothermic, endothermic, huge big idea here. So I always say this, AP Chem is not about knowing a lot of stuff like mediocrely. AP Chem is all about knowing a little bit of stuff really well. This is that little bit of stuff that you need to know really well to have the rest of this make sense. So let's take a look at the energy change that occurs when an ionic compound is formed. So we have to start with something called a formation equation. These are new. We haven't done these before in AP Chem. It's really easy. Formation equations are a composition equation or a synthesis reaction that shows 1 mole, that's important, okay? 1 mole of a compound being formed from its elements in the natural state. So the most important parts I have underlined up here for you. We are talking about 1 mole of product being formed from elements in a natural state. So here's an example, lithium fluoride. So lithium fluoride is LiF. We're creating it right here. We're making 1 mole of it. So in a balanced formation equation, the coefficient on the product side is 1, period. Okay? So you're going to have lithium solid plus F2, fluorine's diatomic, right? Plus fluorine gas yields LiF. It has to balance, all right? So you have to have a 1 here. That's the rule for a formation equation. End of story. So in order to balance that, you need to put a 1/2. I know this doesn't look typical, but it doesn't matter. That's what a formation equation is. You have a 1/2 in front of the F2. Okay, Li plus 1/2 F2 yields 1 LiF. We're going to use that formation equation to do the Born-Haber cycle. Okay, so let's do a couple practice problems. Let's do the formation equation for potassium phosphide and sodium oxide. I'll do the first one, then you can pause it and try the next one. So potassium phosphide is going to be K3P. You need to know your nomenclature. You need to know your charges on your ions. You need to know how to write these, okay? Or else you're going to get all this wrong, right? You need to make sure you know what those ions are. Brush up on them from Chem 1 if you forget. So we want to make that. So let's do this. I'll put my coefficient of 1 already in here. I'm going to put my product. Okay, so I want to form this. Ionic compounds are always solids. It's one of their properties. I want to form this from the elements in their natural state at room temperature. Well, let's start with potassium. Potassium is a solid. You know that because you just do. Okay? So potassium's a solid. It's not diatomic. And phosphorus. Phosphorus, if you look on the periodic table, I want to say that is also a solid. 99.9% sure it is. It's not diatomic. Okay? So, you have K solid plus P solid yields K3P. Let's balance it. You need to put a 3 in front of potassium. Okay, and phosphorus is balanced. There you go. 3K plus P yields K3P. Easy. All right, try sodium oxide. Pause it and give it a shot. All right, sodium oxide. Sodium is Na plus 1. Oxide is O minus 2. So what you're going to get is you're going to have 1 mole of Na2O solid. States are important here. You'll see why in like 2 minutes. So we're going to have sodium plus oxygen. It's O2. It's diatomic gas. Okay. Let's balance it. We need 2 sodiums. We need 1. Oh no, it's a lie. It's 2. No, it's 1. I can't read my writing. You need 1 oxygen, so you need to put a half here. Okay. 2 Na plus 1/2 O2 yields Na2O. Done. Okay. So let's use this to complete the Born-Haber cycle. So here we go. We're going to do the Born-Haber cycle for sodium sulfide. So consider the formation of sodium sulfide in the equation below. So let's write the formation equation in. You can pause it and write it. It's going to look like this. 2Na solid plus sulfur solid yields Na2S solid. Okay? That is our formation equation. So what we're going to do is look at the energy required to make that happen. How do you create sodium sulfide from its elements in their natural state? Here's how we do it. Write the formation equation first, so you know what you're dealing with. Step 1, you want to change everything into the gas form. Okay? So what vocab term is that? That's energy of sublimation or heat of atomization. You might see, depending on what you have, one or the other. Okay? So if you're given the energy of sublimation or heat of atomization, those values will be given to you. If they're positive values, that is an endothermic process. If they're negative values, it's an exothermic process. Well, in order to change something from a solid or a liquid into a gas, that is 100% of the time going to be an endothermic process. Energy is required to make that happen. We learned about that in Chem 1. Let's a quick review of that right now. Okay? So step 1, you're always going to have endothermic process for this. So let's heat up solid sodium to turn it into a liquid then a gas, okay? And same thing with sulfur. And let's track our energy as we do this. So we're going to heat it up. There we go. It's our animation for that. And you're going to turn solid sodium into sodium in the gas state. Okay, so you can see that transition there into the gas state. And that takes 108 kilojoules of energy. These are all going to be given to you. So here's our energy tracker. We have sodium going from a solid to a gas. Look at your equation. You're going to have to write these. So this is really important. Sodium solid plus your 108 kilojoules, because it's an endothermic process, yields Na gas. There's 2 sodiums, though. That's why this is so important to balance your equation. Okay? You have 2 sodiums there. So you need to double that 108. So far we've put 216 kilojoules of energy into this process here. Okay? Now you need to do the same thing for sulfur. Change all elements into their gas form. Okay? So here we go for that. Heating it up, look it up, takes 279 kilojoules, endothermic. So goes from solid to gas. Look at your energy tracker over here. 279 kilojoules times 1 gives you 279 kilojoules. So far we've put in 216 and 279 to turn everything into the gas state. That is step 1. Step 2. Sometimes you will not have to do this. This is one case where you don't have to. But I'm going to talk about it real quick anyway. Step 2, you want to break any existing bonds so you only get single atoms. This is called the bond enthalpy or dissociation energy. You'll see either one. You're also only going to really see this if a diatomic is in use. Okay? There are no diatomics here. Look at your equation. There's none there. So everything's already broken, right? You have two sodium atoms. They're not bonded. They're just close together here because I don't have a lot of room. And your sulfur. Okay? You have three individual atoms. The bonds are broken. If you did have to do step 2, breaking bonds, this is a huge big idea. You have to know this. Breaking bonds is endothermic all of the time. Okay? Breaking bonds, endothermic all day long. Okay? So you're going to have a positive energy value there. Energy's on the reactant side. Okay? So since that's done, let's go to step 3. Step 3 is only going to really focus on the metals here, because you want to remove the electrons to be transferred. So you want to remove the electrons from sodium, right? Those electrons have to move from sodium to sulfur. So let's remove them from sodium. That's called your ionization energy. That's a review of Chem 1. Okay? Ionization energy is the energy required to remove electrons. So let's do that. We're going to put energy in to do that. So energy comes in. Okay, electrons removed. We should do it again. So that took 500 kilojoules. Okay, so again, endothermic. Ionization energy is always endothermic, all day long. So you can see that it's on the reactant side here. So the ionization energy of Na is positive 500 kilojoules. Let's do it again. Okay, same equation. Energy tracker, 500 kilojoules times 2, 1 for each sodium there is 1,000. So a lot of energy going into this so far. That's step 3. Okay, that's taken care of. Now what do we need to do? Well, those electrons now have to go somewhere, right? Well, where do they have to go? They have to go to the sulfur. So the electrons need to be added to the element that wants them. That is the next step, and that is called electron affinity. Okay, so we had one electron go onto sulfur to create S-1. The detail here is so important. We went from neutral sulfur to sulfur -1. Just like on the previous slide, we went from Na neutral to Na +1. Okay, so these small details are key here. Okay, so let's add that electron. You look up the first electron affinity for sulfur. So electron affinity is the energy change when you gain an electron. This is important. This can be positive or negative. It's going to be given to you. Just look at it. Easy. All right? Don't have to worry about if it is or not. Just look what it gives you. So there's our first one. Sulfur plus your electron gives you S-1 plus 200 kilojoules. So in this case, your first electron affinity is negative. Okay? Which is why we write it on the product side. Exothermic for this one. Not always the case, but for this one it is. We still have another electron down here. Let's move it on. Energy released again. Okay, again, sometimes this is endothermic. This case it isn't. Look what happens. You're going to S-2 now. Look at your equation. So please write these down the right way. You have S-1 plus your electron yields S-2. That released 694 kilojoules. Okay? Sodium was the same, the ionization energy, because you took one electron off of this sodium, one electron off of this one. Okay? If you needed to remove another electron from the same sodium, it would be a second ionization energy. Look at what this is. You took one electron, added it to sulfur. That's the first affinity. Then you took your other one and you added it to the same sulfur ion now. Okay? That's why it's your second electron affinity. Okay? So your first one was negative 200 kilojoules. Your second one was negative 694 kilojoules. A million little details here you need to be very careful with and focus on. So don't rush through it. Don't be sloppy. Okay? So if you look at what we have so far, we have a lot of energy changes going on here. The difference between electronegativity and electron affinity is important. So if you remember this from Chem 1, electron affinity is the energy released or gained, okay, it can be either one, when an isolated atom gains an electron. Electronegativity just tells you the ability of an atom to hold on to its electrons or to want electrons, attract them, okay? So just making sure you know the difference between those two things is important. So far, I know I'm in the way here, so sorry. So far, we're at 601 put into this, 601 kilojoules put into this process. But what do we know? What do we know about making ionic compounds? Let's take a look at that. So far, we've put more energy in than we've gotten back. That's not really a favorable process. A favorable process is usually exothermic, okay, in terms of energy, all right? We'll get into some other reasons why endothermic processes are favorable in unit, like a thermodynamic unit, not right now. But in terms of energy, you want that to be a release for something favorable. So what's true about the overall energy change for forming ionic compounds? That's what we're doing here, right? We're making sodium sulfide. Let's take a look at a video clip where we form sodium chloride. And let's see what happens there. What do you notice in that video clip? So we're going to take a look at that right now, then we'll come back to this slide and analyze it.
Sodium metal is heated until it melts and just begins to burn. Then it is immersed into the yellow-green chlorine gas. The sodium begins to burn in chlorine with an intense yellow flame. It produces a white smoke of sodium chloride. We are observing the exothermic reaction of sodium metal with chlorine gas, producing the white solid sodium chloride. Afterwards, the glass spoon contains only white solid sodium chloride.
Okay. So we saw that clip there. We saw a massive exothermic process, right? We saw a massive release of energy. Well, so far, this is not happening, right? So far, we have a total of 601 kilojoules going into it. So we have one step left in this process. We need this whole process to be exothermic, okay? So since we need that to be exothermic, this last step better really make up for the fact that we've put in 601 kilojoules of energy so far. It needs to release at least 602 kilojoules of energy to make this favorable in terms of enthalpy and energy. So let's do it. What's the last thing that needs to happen? Well, you have your sodium plus 1s, you have your S minus 2s. Everything's ready to roll here. All we need them to do is to come together. And that's what's going to happen now. Okay? So your Na plus 1, your S minus 2 comes together. That's your opposites attracting. Energy release. Do it one more time. This energy release is humongous. Okay? That is called the lattice energy. Okay? This is always immensely negative. Okay? Big time negative value, big time exothermic value. So when you write your equation, if you look this up, it's 930 kilojoules. It's a negative 930 for your delta H. So how do you write it? Find your details here. S minus 2 plus 2Na plus yields Na2S. Guess what? It's basically your formation equation, but with your, like, in the ion form here. Like, your ions are coming together now to make this, plus your 930 kilojoules as your energy released. Do your energy tracker, and here's what we get. Your overall change, that's the energy of formation. Okay, it's a vocab term, write that in. Energy of formation. Negative 329. That's what we want. Okay, so we had to turn everything into a gas first. That was step 1. Step 2, we didn't have to do, where you break all your bonds. They were already broken. Step 3, you remove electrons. Step 4, you add electrons. Step 5, you put everything together to form your bonds. This is called the lattice energy here. It's always negative. Something's going to happen in some of your practice problems. You're usually given everything you need in steps 1 through 4. Sometimes you are given the overall change, which is the energy of formation. That's why you have to know your vocab here, okay? Sometimes you are given the lattice energy. You're usually going to have to find lattice energy if you're given the overall, or you're going to have to find the overall, the energy of formation, if you're given the lattice. Students get these two mixed up all the time. So this one and the overall. So just keep that in mind here. Focus on what you need to find. Focus on that vocab. This is easy. So you want to take a second here and label these with the proper vocab term. So you can go ahead and do that from the video, from what we've looked at so far. What do we call all these parts here? So use your vocab. And you can see this is an example of the Born-Haber cycle for sodium chloride. So it's that video we watched. So you're putting energy in to turn everything into a gas. The chlorine was already in the gas state. That's why it's important to make sure you know what your states are. But here we have to do that step 2 where you broke the bond of the Cl2 to make individual chlorine here. Step 3, you have to remove your electrons. Step 4, gain your electrons. Step 5, put it all together. Okay, so take a look at your notes to figure out what those vocab terms are. Here's your overall net reaction formation equation there. You get negative 411. So energy goes in, in, in. In this case, it comes out for step 4, big time out for step 5. And your overall negative 411. That's what we want to see. Okay, summary. Turn everything into a gas, break all bonds, remove electrons, gain electrons, bring it all together. Okay, here's a practice problem you can try. So you can read through this, pause the video, and you will see in a second or two what the correct answer is. So this is important. It says, given the energy of formation, you are given the energy of formation for magnesium fluoride as negative 1123. Find the lattice energy. Okay, that's here. That's step 5. So you know step 1, 2, 3, 4, and the answer, like the final formation. Okay, you don't know step 5. You don't know the lattice energy. That's what you're finding here. So use the information. Sometimes you're given information you don't need. It's to make sure you know what the vocab is and know what you're doing. Find the lattice energy, write your equations, and have your energy tracker. That's what I usually like to do. Okay, equations here, energy tracker here. Figure out what your answers are. Okay, take a second, pause it, see if you can figure it out. Okay, here we go. So you always start with your formation equation. Mg plus F2 yields MgF2. Step 1, turn everything into a gas. Magnesium is the only thing you need to do that for. Fluorine is already in the gas state. Step 2, break your bonds. You only have to do it if it's diatomic. Here we go. Everything has to stay balanced. This is a big mistake here. F2 plus 159 kilojoules yields 2F. Do not screw that up. Okay, you can't take an F2 and just turn it into 1 fluorine. Okay, there's 2 there. Step 3, remove your electrons. This is important here, a little different, a little twist compared to what we did. You have to remove your first electron, ionization energy of Mg. 738 requires that. Now, you're left with Mg plus 1. Now you have to remove your next electron. It's harder to remove that next electron. We've talked about this with Coulombic attraction. Now you have Mg plus 2. That's what you want. Okay? So this was a little different. Look at what you're given. Sometimes you need it, sometimes you don't. Look at step 4. You have to add 1 electron to each fluorine. So you only want to use this. Okay? Electron affinity of F neutral is negative 328. So it's 328 released. Okay? So it's on the product side. That in the equation here, that really shouldn't be a negative value. Okay, it should be a positive value. in your energy tracker, because you never see negative energies in equations, your energy tracker, it's negative. Okay, so I did that here. You have to double your 328 because you have 2 fluorines you're doing this for. So if you want to draw the image like I had earlier, you can do that as well. I won't do the whole thing here. You would Mg and then 2 fluorines, right? So electrons had to go here and here. All right, so you have 2 affinities for, 1 affinity for this fluorine, 1 for this one. So you get negative 656 kilojoules. You know the final formation is negative 1123. Okay, so this is like X. Okay, you're trying to find that. So you have 148, 159, 738, 1450, negative 656, X, and then negative 1123. So this and this and this and this and this and X equals negative 1123. Do some easy money algebra, solve for X, and you get negative 2962. That's what we want to see. Big time negative value. Your lattice energy is always going to be that. All right. Okay, this is a big deal. These take a little bit of time. Once you get used to them, some students actually say they really like doing these because it's the same process over and over again. It's very satisfying once you get your final answer, and it's correct, obviously. So you can give a couple practice problems a try. We'll see how we do on these. So hopefully this made sense. A lot of little concepts and details involved in this. Once you get the hang of it, you'll be in good shape, though. All right, guys, that's it for today. Thank you.